So before I take questions, let me just make a comment in which let me just prove the little identity I used. On the first comment is, we have used delta x dot is equal to delta x dot. And to prove this, let's start with the left-hand side. Delta x dot is limit h goes to 0, delta x t plus h minus delta x of t divided by h. We're using the definition of the derivative. H is not Planck's constant, it's a small real constant parameter. So this is equal to the limit h goes to 0 from the definition of delta x. We can write this as x prime t plus h minus x of t plus h. This is the first guy, minus x prime of t plus x of t. This plus sign is because of this minus sign, divided by h. And then we can rewrite this as limit h goes to 0. We can say x prime t plus h minus x prime of t minus, and within brackets, x of t plus h minus x of t divided by h. And the first term, these two terms divided by h with the limit t equals to 0 is x dot prime of t. And the second one is x dot of t, which is delta of x dot. Okay. All right. So this was something that I used when I did the integration by parts over here, right? When I went from here to here, because we have to write this as the derivative acting on this thing, which is in here. Okay, so this is my proof of the Euler-Lagrange equation. Do we have any questions? Let me make the proof visible a little bit more.
Sir, I have a question.
Yeah.
So in general case, I remember that paths are usually a circular motion of some sort. So is there any?
No. Why would it have to be circular?
Like one particle goes from.
I mean, it can be circular, but it doesn't have to be. I mean, you can throw a baseball, and that's not circular.
I see. Yeah.
Parabolic.
Okay, then just that answers my question. Yeah, there are other cases.
Yeah, there are other cases. But the example I'm going to give you is something which is a periodic system right now.
Yeah, I was thinking of that actually. Yeah, okay, got it.
Any other questions? Okay, so let's give an example. And well, the first example is just Newton's law. So it's so comment number 2 is example Newton's law. So in Newton's law, as we saw, the Lagrangian is half mx dot squared minus v of x. Then delta L by delta x is minus v by x, right? So this is the minus of the gradient of v, which is the force. On the other hand, delta L delta x dot is mx dot. So according to Euler-Lagrange equation, which is delta L by delta x minus d by dt of delta L delta x dot equals to 0. The first term is f, The second term is minus, so if I take it on the other side, it becomes plus. It becomes mx double dot because of this t. And this is exactly Newton's law, right? So let me give you another example. And this is the simple pendulum. Okay. So what is a simple pendulum? We have some ceiling or something, and we have a light rope, and we have a bob, and the bob is and let me draw the vertical, and this is some angle theta, and okay, and this is length L, and this is also length L. Okay. So what is the what is the Lagrangian? The Lagrangian is L is equals to half mv squared minus mgh, right? Because it's potential energy, it's gravitational energy, right? So what is mg? What is h? H is if we can just take this to be 0 height, and this to be, we can set arbitrarily that to be 0. Then then this is then this is h. Okay. So v is going to be L times theta dot, right? Because it's the the arc length. The arc length is L theta. So the rate of change of the arc length is the speed, right? Is the tangential speed. And h, on the other hand, is this length minus this length, which is L minus L cosine of theta. And we're going to take the small theta limit, as is usual for simple pendulum. Then we can factor out L here. We get 1 minus. And let's just expand cosine of theta as a Taylor series up to the second order, 1 minus theta squared by 2, right? Then if I write this, then these two terms cancel out, and this minus minus gives me plus. I get L theta squared by 2. So I put all of this together in my Lagrangian, and then my Lagrangian becomes half of m L squared theta dot squared minus half mgl theta squared. Right? And if I now work out the Euler-Lagrange equation, this is, now here's the important bit. The coordinate here is not the xy coordinate of the particle. The relevant degree of freedom here is the angle theta, right? So although it's a two-dimensional system, it's actually, that's an illusion. It actually has only one degree of freedom, and therefore it's actually a one-dimensional system. But the correct variable is not x and y. We go to the polar coordinates, and theta is the correct variable. Did someone say something?
No, sir. I was just switching devices, and yeah,
okay, no
something happened.
So del L by del theta dot, that is my Euler-Lagrange equation. And if I do this, I get the first term is mgl theta from this guy, and the second term with a plus sign is is m L squared theta double dot is equal to 0. And we can cancel one of these guys out. We can cancel the m out. This is, of course, it's a famous cancellation, right? This cancellation of two m's are famous, right? Can somebody tell me why it's famous?
The equality of the gravitational mass and the Newton.
Exactly, because the mass here is the gravitational mass, and the mass here is the inertial mass. And the fact that they are equal was a puzzlement, a source of puzzlement to Newton. So Newton did a lot of experiments with different material to see if this m could be changed. And he found that no, it's not. It's always the same within experimental limits. And of course, this was only resolved by Einstein's principle of equivalence, which is the cornerstone of general relativity, right? All right, so our differential equation then becomes theta double dot plus g by L theta is 0, right? And we can look for a solution to this. The solution is theta is, say, some constant a times exponential of I b of t, say, plus 5. And so if I take theta dot, I get I a b e to the, or I, let's just say, okay, if I do theta dot, I get I b theta, right? And if I do theta double dot, I get minus b squared theta. So that means that if I compare this equation with this equation, that means that b squared is g over L, and therefore b has to be square root of g over L, right? Which is also called omega, because it has the dimension of frequency, because g is length per times divided by time squared, and there's a length here, so the length cancels out, the square root gives you 1 over time. And therefore, we can take the real part of this guy to be the solution, and then our solution is, I can rewrite a to be theta naught, and the solution then is cosine of omega t plus phi, right? So we all know this. All right, so let's make some comments. Any question about the derivation?
No, sir.
Okay, so let me make some comments, and the first one is the important one, that note that the coordinate in this case is theta and not x comma y. So theta is known as a generalized coordinate. Okay. And it can be anything, as long as its dimension doesn't have, theta is dimensionless in this case, right? Because theta is an angle measured in pi radians, so it doesn't have any dimension. And then theta dot is called the generalized velocity. Okay, so number 2 is that the generalization to multi-particles is immediate. So suppose you have n particles. Let's say you have n degrees of freedom. Let's not even call them particles. Then you have n kinetic terms, and not all these masses have to be different, and some potential. And then you derive Euler-Lagrange equation for each degree of freedom, each generalized coordinate, you get the Euler-Lagrange equation. And again, this is the generalized velocity, or right? Okay, number 3 is the Euler-Lagrange equation is a second order differential equation, right? Because you got time derivative, and remember that L itself has first derivative of Q. So you would get, in general, a second order differential equation. Right? So to solve it, now to solve a system with, say, n generalized coordinates, you need, say, 2 n boundary conditions, right? And these boundary conditions can be all the coordinates at some initial time t0 and all the coordinates at some final time tf, or it can be, the coordinate at t0 and the velocities at t0, right? Just as you expect for Newton's law. So I think this concludes my treatment of the Lagrangian formulation of classical mechanics. In the next class, before we go on to the path integral formulation of quantum mechanics, I want to give you a short treatment of the Hamiltonian formulation of classical mechanics, which is also very useful. Any questions?